Welcome everyone. Today, we'll walk you through the key degradation threats that affect seawater systems and understanding internal and external corrosion mechanisms, based on a schematic overview of typical system components and associated risks. This diagram, references of degradation threats to the seawater systems is from Corrosion Threats Handbook, Upstream Oil and Gas Production Plant, Energy Institute. Overview of the seawater system. The seawater system is critical in many industrial applications, especially offshore. It includes components like lift pumps, filters, derators, heat exchangers and injection wells. Each part is vulnerable to specific degradation threats. Key points: seawater lift pumps to injection wells. Key components: filtration, deaeration, pumps, heat exchangers. Importance in offshore and industrial operations. Classification of degradation threats. Threats are categorized as internal or external. Internal threats are chemical or biological, while external threats include mechanical damage and environmental corrosion. Key points: internal threats, in red on this diagram, originate from within the system. External threats, in blue on this diagram, environmental or mechanical. Total of 14 major threat types. Internal threats. Chemical corrosion. Chemical corrosion is a major concern. Carbon dioxide corrosion or CO2 and hydrogen sulfide corrosion or H2S create acidic conditions, while oxygen and microbes accelerate metal degradation. Key points: carbon dioxide corrosion or CO2 corrosion, acidic environment from dissolved CO2, hydrogen sulfide corrosion or H2S corrosion, sulfide stress cracking, oxygen or O2 corrosion, accelerates rusting. Microbially influenced corrosion or MIC, bacteria-induced corrosion. Internal threats. Localized corrosion. Localized corrosion often occurs at joints, welds, or where flow is restricted. These areas are prone to rapid material loss if not monitored. Key points: galvanic corrosion is a corrosion caused of dissimilar metals. Weld corrosion occurs at heat-affected zones. Grooving crevice corrosion occurs at stagnant zones. External threats. Environmental. External threats are often underestimated. Corrosion under insulation or CUI is particularly dangerous because it's hidden and hard to detect. Key points: external corrosion is a corrosion caused of atmospheric exposure. Corrosion under insulation or CUI is a corrosion caused of moisture trapped under insulation. Stress corrosion cracking or SCC is a corrosion caused of cracking under stress and corrosive environment. External threats. Mechanical miscellaneous. Mechanical degradation like erosion and fatigue can lead to sudden failures. Miscellaneous threats like liquid metal embrittlement or LME are rare but catastrophic when they occur. Key points: erosion, erosional corrosion, high velocity flow, fatigue, fretting, vibration and movement, liquid metal embrittlement or LME, acid corrosion, rare but severe. Threat mapping on system components. Each component has its own vulnerability profile. For example, pumps are prone to erosion and microbially influenced corrosion or MIC, while pipelines are at risk of stress corrosion cracking or SCC and external corrosion. Key points: pumps usually has credible threats such as erosion, microbially influenced corrosion or MIC, and galvanic corrosion. Filters usually has credible threats such as crevice corrosion and oxygen corrosion. Derators usually has credible threats such as carbon dioxide corrosion or CO2 and oxygen corrosion or O2, and pipelines usually has credible threats such as external corrosion and stress corrosion cracking or SCC. Mitigation strategies. Mitigation involves a combination of design, materials, and maintenance. Regular inspections and proactive monitoring are key to preventing failures. Key points: material selection and coatings, cathodic protection, chemical dosing, biocides, oxygen scavengers. Regular inspection and monitoring. Detailed mitigation strategies for internal threats. If the internal threats type is carbon dioxide corrosion or CO2, then the internal threats mitigation for CO2 corrosion are: use corrosion-resistant alloys such as duplex stainless steels. Apply internal coatings or linings. And control CO2 levels via deaeration or chemical treatment. If the internal threats type is hydrogen sulfide corrosion or H2S, then the internal threats mitigation for H2S corrosion are: use H2S resistant materials such as NACE MR0175 compliant. Apply cathodic protection. And monitor and control H2S concentration. If the internal threats type is oxygen corrosion or O2, then the internal threats mitigation for O2 corrosion are. Install derators to remove dissolved oxygen. Use oxygen scavengers such as sodium sulfite. And maintain closed-loop systems where possible. If the internal threats type is microbially influenced corrosion or MIC, then the internal threats mitigation for MIC corrosion are regular biocide dosing such as glutaraldehyde, THPS. Periodic pigging and cleaning. And monitor microbial activity, biofilm sensors, ATP testing. If the internal threats type is galvanic corrosion, then the internal threats mitigation for galvanic corrosion are electrically isolate dissimilar metals. Use sacrificial anodes or impressed current systems. And match materials with similar electrochemical potential. If the internal threats type is weld corrosion, then the internal threats mitigation for weld corrosion are use proper welding techniques and post-weld heat treatment. Select compatible filler materials. And inspect welds regularly for early signs of attack. If the internal threats type is grooving crevice corrosion, then the internal threats mitigation for grooving crevice corrosion are avoid stagnant zones in design. Use welded joints instead of flanged or threaded ones. And apply sealants or gaskets to minimize crevice formation. If the internal threats type is erosional corrosion, then the internal threats mitigation for erosional corrosion are reduce flow velocity and turbulence. Use erosion-resistant materials such as Inconel, ceramics. And optimize pipe routing to avoid sharp bends. Summary of mitigation strategies. Internal threats. Internal threats are best managed through material selection, chemical control, and good design practices. For example, derators and oxygen scavengers help reduce O2 corrosion, while biocides combat MIC. Key points. For chemical corrosion such as CO2, H2S, and O2 use resistant alloys, deaeration, chemical dosing. For MIC corrosion use biocide treatment, pigging, microbial monitoring. For localized corrosion such as galvanic, weld, groove and crevice use material compatibility, proper welding, designed to avoid stagnation. Detailed mitigation strategies. External. If the external threats type is external corrosion, then the external threats mitigation for external corrosion threat are apply protective coatings such as epoxy and polyurethane. Use corrosion-resistant cladding. And implement cathodic protection. If the external threats type is corrosion under insulation or CUI, then the external threats mitigation for corrosion under insulation or CUI corrosion threat are use water-repellent insulation materials. Apply CUI-resistant coatings such as silicone-based. And regular inspection using NDT such as radiography and UT. If the external threats type is stress corrosion cracking or SCC, then the external threats mitigation for stress corrosion cracking or SCC corrosion threat are select SCC-resistant materials. Reduce tensile stresses via stress relief treatments. Control environmental factors such as chloride levels. If the external threats type is fatigue and fretting, then the external threats mitigation for fatigue and fretting threat are minimize vibration and cyclic loading. Use flexible supports and dampeners. And apply surface treatments such as shot peening. If the external threats type is liquid metal embrittlement or LME, then the external threats mitigation for liquid metal embrittlement or LME threat are avoid contact between susceptible metals and liquid metals. Use barrier coatings or liners. Control process temperatures. If the external threats type is acid corrosion, then the external threats mitigation for acid corrosion threat are neutralize acidic environments with chemical dosing. Use acid-resistant materials such as Hastelloy and PTFE. Monitor pH levels continuously. Summary of mitigation strategies. External threats. External threats often require physical barriers and structural design improvements. CUI, for instance, is mitigated with specialized coatings and regular inspection under insulation. Key points. For external corrosion CUI, mitigation strategies can be used are such as protective coatings, cathodic protection, water-resistant insulation. For stress corrosion cracking or SCC, mitigation strategies can be used are such as stress relief, chloride control, resistant materials. For mechanical threats such as erosion, fatigue and LME, mitigation strategies can be used are such as flow control, vibration dampening and surface treatments. Summary of mitigation approach: there's no one-size-fits-all solution. A layered approach combining prevention, detection, and response is the most effective way to manage degradation threats in seawater systems. Key points: Number 1, combine material science, chemical treatment, and design optimization. Number 2, implement monitoring and inspection programs. And number 3, tailor strategies to specific system components. Inspection methods for internal threats: if the internal threats type is carbon dioxide corrosion or CO2, then the inspection or monitoring methods can be used are UT, radiography, corrosion probes or corrosion coupons, intelligent pigging, process parameter monitoring. If the internal threats type is hydrogen sulfide corrosion or H2S, then the inspection or monitoring methods can be used are UT, radiography, dye penetrant, eddy current, process parameter monitoring. If the internal threats type is oxygen corrosion or O2, then the inspection or monitoring methods can be used are UT, radiography, corrosion probes or corrosion coupons, oxygen scavenger residual monitoring. If the internal threats type is microbially influenced corrosion or MIC, then the inspection or monitoring methods can be used are UT, radiography, microbial and sulfate sampling, biostuds or sidestream monitoring. If the internal threats type is galvanic corrosion, then the inspection or monitoring methods can be used are UT, radiography, visual inspection, material compatibility checks. If the internal threats type is weld corrosion, then the inspection or monitoring methods can be used are UT, radiography, online monitoring with welded probes. If the internal threats type is grooving corrosion, then the inspection or monitoring methods can be used are intelligent pigging. Monitoring of influencing parameters such as CO2, O2, MIC, and erosion. If the internal threats type is crevice corrosion, then the inspection or monitoring methods can be used are visual inspection, especially during maintenance, planned and opportunistic inspections. Inspection methods for external threats. If the external threats type is external corrosion, coatings, fasteners, then the inspection or monitoring methods can be used are visual inspection, CP potential monitoring/survey. If the external threats type is corrosion under insulation or CUI, then the inspection or monitoring methods can be used are visual inspection, strip and search, real-time radiography, thermography, pulsed eddy current. If the external threats type is stress corrosion, cracking or SCC, then the inspection or monitoring methods can be used are eddy current, dye penetrant, UT, radiography, visual inspection. If the external threats type is erosion, then the inspection or monitoring methods can be used are UT, radiography, acoustic probes, intrusive erosion probes, corrosion-resistant coupons. If the external threats type is erosion corrosion, then the inspection or monitoring methods can be used are UT, radiography, corrosion monitoring, process parameter monitoring. If the external threats type is fatigue and fretting, then the inspection or monitoring methods can be used are visual inspection, radiography, vibration monitoring. If the external threats type is acid corrosion, then the inspection or monitoring methods can be used are UT, radiography, corrosion probes or corrosion coupons. If the external threats type is liquid metal embrittlement or LME, then the inspection or monitoring methods can be used are dye penetrant, magnetic particle inspection or MPI. Summary of inspection methods. Each degradation threat has specific inspection techniques. For internal threats like CO2 or MIC, we use UT, radiography, and corrosion coupons. For external threats like CUI or SCC, we rely on visual inspection, thermography, and advanced NDT like pulsed eddy current. Key points: for internal threats, inspection methods can be used are UT, radiography, corrosion probes, microbial sampling, and intelligent pigging. For pipelines, for external threats, inspection methods can be used are visual inspection, thermography, pulsed eddy current. Final summary: to wrap up, remember that managing degradation in seawater systems is not about one solution, it's about integrating prevention, detection, and response. A proactive approach ensures safety, reliability, and cost efficiency. Key points: Number 1, seawater systems face multiple degradation threats, both internal and external. Number 2, mitigation requires a combination of material selection, chemical treatment, and design optimization. Number 3, inspection and monitoring are essential for early detection and prevention of failures. And number 4, a layered integrity strategy ensures long-term system reliability and safety. Top 10 frequently asked questions for degradation threats in seawater systems. Question number 1. What is the most common internal corrosion threat in seawater systems? Answer: oxygen corrosion or O2 and microbially influenced corrosion or MIC are among the most common due to the oxygen-rich and biologically active nature of seawater. Question number 2. How can we detect early signs of MIC or microbially influenced corrosion? Answer: through microbial sampling, biostuds, sidestream monitoring, NUT, or radiography for physical damage. Question number 3. What inspection method is best for detecting corrosion under insulation or CUI? Answer: strip and search, thermography, and pulse steady current are effective for detecting CUI without full insulation removal. Question number 4. How do we differentiate between erosion and erosion corrosion? Ans. Erosion is purely mechanical wear, while erosion corrosion involves both mechanical and chemical attack. Inspection includes UT, radiography, and erosion probes. Question number 5. What makes galvanic corrosion more likely in seawater systems? Answer: the presence of dissimilar metals in a conductive electrolyte like seawater, especially at welds or fittings. Question number 6. Which components are most vulnerable to weld corrosion? Answer: heat-affected zones, HAZ, poorly executed welds, and areas exposed to CO2, O2, or acidic environments. Question number 7. How often should intelligent pigging be performed for internal corrosion monitoring? Answer: frequency depends on risk assessment, but typically every 3 to 5 years for high-risk pipelines. Question number 8. Question: what are the signs of stress corrosion cracking or SCC? Answer: branched or intergranular cracks, often near welds or areas of high stress. Detected via dye penetrant, eddy current, or UT. Question number 9. Can coatings alone prevent external corrosion? Answer: no. Coatings must be combined with cathodic protection and regular maintenance for effective long-term protection. Question number 10. What's the best strategy to manage multiple degradation threats simultaneously? Answer: implement a risk-based inspection or RBI program, use corrosion-resistant materials, and apply layered mitigation, chemical, mechanical, and design-based. Thank you.